And this year we have Jean-Pierre Luminet from the Observatoire de Paris, who is speaking on the early years of black hole imaging, his personal reflections. And before I invite him to speak, I just wanted to say a few words about Jean-Pierre. He is a French astrophysicist, writer and poet, specializing in black holes and cosmology. He works as the research director for the CNRS, the Centre National de la Recherche Scientifique. My French is not as good as my mother's. Is a member of the Laboratoire Universe Theories, LUTH, at the University, the Observatory of Paris-Meudon. And he also serves on the editorial board of the Astronomical Review. There is an asteroid actually called after him, number 5523. And in 1979, as he will describe, he created the first image of a black hole using nothing but an early computer, lots of math, and ink. So he basically produced the image based on calculations, and then the intensity of the image was drawn according to his calculations. And that was really the very first image. And we are thrilled to have Jean-Pierre give the banquet speech.
Thank you, Avi. Good evening. I am deeply, very grateful to the organizer of the conference for inviting me, and especially to Shep Dolman, with whom I had previously enjoyable email exchanges. And I am much honored to have the privilege to give the keynote talk with my terrible French accent. Well, the first part of it is based on a paper that I recently put on the archive in March. No, it was the wrong way. Sorry, I made a bad movement. This is really a black hole.
There you go.
Oh, okay, sorry. Yeah, no. Yeah. It was the wrong button. We have to say that I'm a little bit tired because in Sunday I was still in the south of Italy. I had a 12-hour drive by car to come to Marseille and take the plane yesterday morning to arrive yesterday in the evening. But now I'm so glad to be among you to tell the story of black hole imaging. So the first part of my talk is about the history of black hole imaging. Since I began to address the question 41 years ago, at a time when most of you were not even born. So I'm a kind of dinosaur of the story, but not yet extincted. And the second part will be a surprise. Okay. I recall that in the beginning of the 1970s, we had already a good theoretical framework for describing black hole physics and geometry, thanks to the pioneering work of John Wheeler, Stephen Hawking, Roger Penrose, Brandon Carter, Raymond Ruffini, and many other people. But we had only very indirect evidence for their real existence of black holes. For instance, we had the guess that we could have stellar mass black holes in binary X-ray sources, and as you know, we had to wait the launch of X-ray telescope in space, like the first one was Uhuru in 1971, who checked that, well, we had the first good stellar mass black hole candidate, which was Cygnus X1. We had the guess that from pure energetic consideration for quasars and active galactic nuclei suggested by Lindenbell and Rees in the beginning of the 70s, that we should have a kind of engine to produce to release a lot of gravitational energy in order to explain the huge amounts of energy observed in quasars and active galactic nuclei. And as you know, we had the idea from Balik et al. That we had a compact radio source in the galactic center, probably associated to a massive black hole. Okay, so if the black hole itself remains invisible, in fact, it lights up in a very special way the matter it attracts. So logically, the astrophysicists wonder what a black hole surrounded by luminous matter would look like at the scale of the event horizon. The day we would have a huge and high-resolution telescope, or the still remote day when we can travel in interstellar space and explore a black hole neighborhood. So in the meanwhile, the basic feature of black hole imaging could be calculated by computer simulation. And the first calculation for a Kerr black hole was not done, as it is usually said by John Bardeen, but by Godfrey. In 1970, Godfrey published in Physical Review this paper, what is never quoted, where he made the first images of the cross-section, the photon capture cross-section for black holes with various angular momenta. So you recover the special case of Schwarzschild black hole, non-rotating black hole with 0 here, which is, of course, a perfect sphere, and slightly distorted event horizon with increasing angular momentum here. So generally, it's, we refer to the work of Bardeen in 1972. We calculated the apparent shape of the event horizon of an extremely Kerr black hole with very high angular momentum. So in fact, Bardeen is the only guy to quote the previous paper by Godfrey. But as he told that after the rest of the mathematics was completely wrong, so the paper by Godfrey was forgotten in the literature. But at least the picture was correct. So it was presented by Bardeen in a famous talk at Les Houches, the summer school of Les Houches. And Bardeen had a PhD student named Cunningham. So they started to make some calculation, not yet of an accretion disk, but just the calculation of the orbit of a star in circular orbit around an extreme Kerr black hole. So here you have the first figure showing the circular or distorted circular orbit around the Kerr black hole with a star. So you have here the primary image. And here, the secondary image, the scale unit is here. So it's the size of the event horizon. And here you have two different views. The first one at polar angle of 84 degrees. And you have the radius at 20 in scale of this unit. And here, a much closer circular orbit at 3. GM over c square with the same polar angle. So this is the shape of a star circular orbit. And they also calculated the variation of luminosity, amplification of light by gravitational lensing, just of this punctual star marked here with the numbers. Okay. So now I go back to my personal recollection. So after my studies in Marseille in pure mathematics, in 1976, I moved to Paris Meudon Observatory to get a PhD, not at all on black holes. It was on singularities in some strange models of general relativity. and my advisor was Brandon Carter. And as you know, Brandon Carter was one of the main contributors to black hole theory, and especially to Kerr geometry. Just after my PhD, Carter suggested me to calculate a realistic image of a black hole surrounded by a thin accretion disk. Of course, I liked very much the idea to show for the first time the invisible in some way, because it had never been done previously, and because also I was surrounded at Paris Observatory mostly by classical astronomers who did not believe in the existence of objects that they could not see. So it was an interesting challenge, of course, to show the invisible. Well, before, it was always my philosophy in my later work, before beginning numerical calculation, writing a program, it's necessary to have before an idea of what you would get by geometrical consideration, for instance. So to have the rough idea of the image of the circular luminous rings around the spherical body, well, you have the classical image. Oh, sorry. Okay. You have the classical image in a flat space-time with Saturn, with, of course, a part of the rings, which is hidden behind the main disk. But, well, just a very simple geometrical consideration tells you that instead of Saturn, you have a black hole, you have a thin accretion disk. Of course, you will not have hidden part of the accretion disk because the rear part will be, due to the bending of light, of course, will be entirely visible to a photographic plate at large distance. So you will have, you can guess you should have this kind of image for the top of the disk, distorted from ellipses, of course. And you should have also a secondary image because some of the light rays are still more bent by gravitational field. And you can have the image of the other side of the accretion disk, very distorted one. So you have the top of the disk and the bottom of the disk. And in fact, theoretically, you can have an infinite number of images depending on the wrapping of the photon around the event horizon. Okay, so I started the calculation in the beginning of 1978. So I spent just a few weeks to write the equation, and I achieved the work in the summer of 1978, and it was published in Astronomy and Astrophysics in January 1979. So some details of my calculation. Well, first of all, I just put this figure. We illuminate a black hole, and you have, of course, an enhancement factor due to the capture of light, and we recover the well-known factor, which was known for decades, the square root of 27. So for a Schwarzschild black hole, you have an enhancement factor of the horizon, the size of the horizon, the apparent size of the horizon, which is the black hole shadow, will be enhanced by a factor 2.6, all right? And well, you have the return of light, which is in fact the photon ring, which is here, shown here in this calculation. I call that the glory, in fact, by reference in a phenomenon well known in traditional optics. You know, in traditional optics, you can have sunlight which is scattered by a large number of water droplets in mist. And it is sometimes possible to see in reflection the shadow of one's head surrounded by brilliant rings of light centered on the line of sight. So it's called the glory. It's a good term to describe this halo of light, this what we call now the photon ring. So after that, I start the calculation while using the only available computer at the time at the Meudon Observatory. It was a mainframe IBM 74, something like that, with transistors, a punch card, and all that. No visualization software. Well, the first step, of course, is just to write the equation, integration of photon trajectory in the Schwarzschild matrix. Okay, calculate now, depending on the impact parameter, all the photon orbits. And the first calculation gives just the isoradial curves. Well, just the same thing that Bardeen had done just for a circular orbit around a Kerr black hole. This is just a series of circular orbits, depending, of course, of the angle of view, with the primary image of the circular rings. Here you have the distance, and here you have the secondary image. So this is the view angle with respect to the plane of the accretion disk of 30 degrees, and here an angle of only 10 degrees. Okay, so you recognize this typical shape of kind of a mushroom, something like that. Well, this is just a pure geometrical distortion. Now I wanted to get a more or less realistic image, so take into account the physical properties of an accretion disk. So I took the physical model of a thin accretion disk, in fact, geometrically thin and optically thick accretion disk models by Shakuran, Sanayev, and Page, and so on. So we had the intrinsic flux, bolometric, all these are integrated on all wavelengths, depending on the accretion rates and all that. So just the simple model says that the intrinsic flux is maximum at this about 10 Schwarzschild radii. Okay, after that we have to take into account all the redshift effects, two kinds of redshift effects, the Einstein effect, of course, from the gravitational field, and mostly the Doppler effect due to the relativistic motion of the disk around the black hole. So this is just the formula. All right. And finally, step 4, just to have the apparent flux for a distant observer. That's all. So you have, I could get, with the drawing software, the only drawing software we had, I could draw the curves of constant apparent flux, depending on the angle of view. Okay. So the number here are just in units of the maximum intrinsic flux, okay? And this is the apparent flux in units of that. And you see that, of course, this is the part where the Doppler effect is the most important, the part of the disk approaching from the observer, so you have an amplification of light. So all these curves were presented in my article in astronomy and astrophysics, but of course the final picture, which was a more or less realistic picture, was that one. So the paper was called The Image of the Spherical Black Hole with Thin Accretion Disk, so published in January in Astronomy and Astrophysics. So I repeat that it's geometrically thin disk, but optically thick, so it's the reason why we see, so you see here the black hole shadow, of course, enhanced by the factor 2.6 compared to the real size of the event horizon. Here you have the primary image, namely the top of the accretion disk. Here you have the last stable circular orbit, because as you know, in Schwarzschild spacetime, the inner edge of the accretion disk is at some distance from the event horizon. Here you have the secondary image, namely the other side of the accretion disk, but which is in fact the equivalent of the photon ring. And here you have the part of the accretion disk which is strongly enhanced by the Doppler effect because the rotation of the disk is like that. So this is the approaching part, and this is the receding part. So now it has been told that I made this drawing by hand just because we had no visualization software. So what I did exactly, well, I started with, I had this. So I printed a large copy of that. I put on this transparent paper, and I put by hand with Indian ink a number of points with black ink, with Indian ink proportional to the flux. So I put by hand about 10,000 points, something like that. Okay. So in fact, it was the easiest part of the thing. It was not very difficult, just a little patience. I took maybe 1 day, not more. Okay. So you can see from that, I put by hand, and I get this, this picture. Okay. So in fact, the picture was first shown not in the astronomy and astrophysics paper, but in a popular French magazine, which is called La Recherche, with more or less the equivalent of Scientific American, where in fact we were told to write the first popular paper on black holes with Brandon Carter. And as I just got this image, so we added this image. So it was published for real the first time in November 1978, 41 years ago. And after the technical paper with all the detail and the equation in January 79. Just at the end of the paper, I would just want to enhance this this sentence that already we predicted that maybe this kind of picture would be could represent some sources like M87, because already at the time, well, we had some indication of the presence of supermassive black holes in. So it was, as I told you, it was not a great job to just put thousands of points, black points, because at the time I was practicing for many years lithography and drawings with Indian ink, and usually I made a drawing much more complicated than that. And at the same time, I produced a lithography called the black hole, but which was my own interpretation, nothing scientific, pure artistic view, which was that one. So you can guess that it's much more difficult, and I took several months to do this and not just one day. So of course it's completely metaphoric, because here you have a kind of cathedral, which is can represent Newtonian physics, which okay, and here you have a kind of optical illusion with here the pavement which looks curved, negatively curved, but in fact it's just a pure optical illusion. It's perfectly right, but I introduce well, some perspective which attracts the look to the bottom. And so here you have, of course, the symbol, the metaphor of the black hole. And I already introduced the idea that quantum mechanics, represented by dice, could play a fundamental role in the physics of black holes. And in fact, this picture was used at the cover of my first book on black holes, which was published first in French and after in Cambridge University Press, in which I have one chapter devoted to the picture of black hole that I showed you. So now I continue the story. In fact, the first, so nobody happened for about 10 years. The first non-bolometric image was produced by two young Japanese guys, Fukue and Yokohama, in 1988, We calculated for a stellar mass Schwarzschild black hole the shape and the color with depending of temperature, with a special coding, of course, of an accretion disk. So, for instance, for a stellar mass, you had this kind of temperature. So you have here false color, of course. It is bolometric, and this is the X-ray band, and this is the optical band. And they also calculated a picture for a supermassive black hole. Okay. Now I had a collaborator called Jean-Pierre Luminet, who was very gifted for numerical simulation. And in 1989, while I spent 1 year in Berkeley working on completely different subjects like cosmic topology, I suggested to Jean-Pierre, who stayed in Paris Observatory, to use well, the modern computer to produce new image in color and also animated image. And I show you another published image, which is that one, with different angles of view of a Schwarzschild black hole, with all the Doppler effect took into account. Okay, so you see the primary image, and you see the secondary images of photon ring at the center. When I went back to Paris, I told to Jean-Pierre Luminet to produce animated image. Essentially, to make a movie, a documentary on black holes for the French television. So Jean-Pierre performed some fantastic numerical simulation, taking account diffusion effects in accretion disk, all the physics. So I show you some pictures of Jean-Pierre Luminet. So this is a colored image of a Schwarzschild black hole accretion disk, with an inclination angle of 7 degrees. So you have the Doppler effect, the primary image. The secondary image, the disk is slightly slightly optically seen, so you can see the guess of the secondary image here. Okay, with the background star. After that, I asked to Jean-Pierre, for the needs of the movie, to calculate a flight into a Schwarzschild black hole along a plunging trajectory, starting very far from the black hole, crossing the plane of the accretion disk, and finally finishing inside the black hole. And step by step, we calculate the landscape. Okay? Always using the equation of general relativity. It's not at all an artist view. Really, numerical calculation. So away from the black hole, we recover the expected image. Here we cross the accretion disk. Here we are in position 5, position 6, position 7. So here, for instance, you see not only the secondary image, but the tertiary image, very thick on the event horizon, enlarged event horizon. And as soon as we approach very closely to the event horizon, we see more and more distorted image of the accretion disk, multiple images. And the final image is inside the black hole. We just turn to see the outer universe. And we still see something, of course, because light comes into the black hole. And we can see the very distorted shape of the accretion disk. Finally, I asked to Jean-Pierre to make a full movie for this kind of trajectory. So this is a flight around a Schwarzschild black hole with elliptical orbit with all the precision effects. So we will cross several times the accretion disk, and this gives this movie that was shown in the TV documentary, which is that one. So you can see the disk is not optically thick because we can see in transparency some stars through the disk. Okay, so we have done several turns crossing the black hole. So probably you had never seen these fantastic images. One of the reasons is that at the end of the 90s, Jean-Alain Marc brutally died from a cancer at the age of 40. And as he calculated all the things on a personal computer, nobody could never find his programming code. So the only remaining is just this picture animation of the movie, and I could recover this image for you. So it's one of the reasons why this extraordinary work by Jean-Alain Marc remains mostly unknown, is never quoted in your papers. Of course, some of you have seen the simulation of a black hole in Interstellar movie. So just for the fun and the anecdote, Kip Thorne wrote me a special email before the release of the movie on the screen. I was not aware that he was preparing a movie. Okay, so he told me, Jean-Pierre, if you go to the cinema, if you see my movie, don't be shocked that the image that is presented in the media as it is the best ever simulation, black hole simulation, doesn't take into account the basic feature of the Doppler effect, because when I proposed that to the filmmaker, Christopher Nolan, he didn't want at all to have this, because well, he was thinking that people would understand nothing to that. Well, I'm not sure that they understood something in the movie, but well, okay. In fact, this configuration we had already calculated in a purely realistic way with Jean-Alain Marc, and we published in a popular magazine. We are exactly in the plane, so you exactly recover the image, a distorted image, the pure geometrical distortion. But here you have really all the diffusion effects of the accretion disk, the Doppler effect, and all that. Okay, now, well, after that, I worked on completely different subject, but well, the work of visualization of black hole accretion disk went on. So the first accretion disk imaging for a Kerr black hole, mostly extreme Kerr black hole, was done by Virgutz in 1983. So it's more or less a generalization of the Bardeen calculation. It's not a very realistic image, but well, the calculation is at least correct according to the law of general relativity. We have also some simulation by Fenton at Galvani and other guys, and by Bromley. Okay, so here you see, for instance, these lines are the lines of zero redshift. Okay, so here you have a Doppler effect increasing the apparent flux, and here you have the Doppler effect decreasing. The same here. Okay. So, well, I stopped just the early story of black hole imaging. It's really poor, not much simulation, because, well, when the VLBI EHT projects began with the paper, the basic paper by Falk and Melia, by Shep, well, at the beginning of the century, well, there was a blooming of numerical calculation. So when I see that just for your calculation, you have an image library with 60,000 fixture, of course, it's a completely different story, including magnetohydrodynamics and all that. So for instance, well, I could check, well, I didn't follow exactly, I will explain why this story, but well, I rediscovered, in fact, the project through the paper in Scientific American with some simulation by Broderick and Loeb, like here. So we recover, of course, the initial shapes that I calculated previously. Okay. In fact, what was I doing during this time? So I didn't follow more the history of black hole imaging, because in fact, in the decades of 1980, I was one of the first to work about the tidal disruption of stars by supermassive black hole, which was another way to have indirect signature of the presence of black holes in the center of galactic nuclei. So in first paper was published with Ballon Carter in Nature, and we predicted a kind of what we call the tidal supernova, namely the strong crushing of stars which penetrate deeply inside the tidal radius in a kind of a pancake configuration, and with a thermonuclear detonation of the star just by the external gravitational field, tidal field. So I worked after that with some students to develop all these models, which have been observed later. And also after, in the next decade, I worked essentially in cosmology, in cosmic topology, and I proposed, for instance, in 2003, a special model for the shape of space, finite space with a dodecahedral space topology, finite space without a boundary, and we made the cover of the Nature. Okay, so it's one of the reasons why I didn't follow very closely the progress, fantastic progress in the LBI observation. And of course, now this final image. Well, in fact, I was always a rather self-solitary researcher, doing my work either alone or with one or two collaborators, no more. So I am really deeply admirative to people able to build and to manage great scientific projects involving dozens of institutes and hundreds of researchers all around the world with no guarantee of success. So it was already the case with LIGO-Virgo collaboration, leading to the first detection of gravitational waves, and it is now the case with the EHT program. And I am really deeply moved to be here in the very heart of the Black Hole Initiative, and sees, thanks to all of you, one of my dreams become a concrete reality 40 years later. So normally I should have stopped here if I had no ordinary talk, but as I have the privilege to have a little more time, I had something new. You see, you know that we can also have an idea to show black hole not surrounded by accretion disk, just naked black hole, but which have an effect just by gravitational lensing on a background sky. And one of my collaborators, which is called Alain Riazuelo, who is working at the Institut d'Astrophysique de Paris, with whom I collaborated for cosmic topology, I asked him also to make some simulation, very realistic simulation of gravitational lensing of black holes. Because in fact, there is really a French school of black hole imaging. So for instance, here you have a map, star map, real star map of the southern hemisphere with the Milky Way, something like that. So Alain calculated what would like this picture if on the line of sight here you have a black hole. Okay? So this is the result of the calculation. Of course, the primary image is distorted in the vicinity of the black hole. You have a secondary image which shows the full Milky Way, and not only the part of the Milky Way in the field. Because, of course, as we know, we have the ancient ring, theoretical ancient ring. And inside the ancient ring, as you know, the full universe is duplicated, entirely duplicated. So all the external universe, all the celestial sphere, is entirely duplicated and strongly distorted, of course, inside the ancient ring. So more spectacular now, we imagine always with this nice view of the southern hemisphere. You recognize the Magellanic Clouds here, the Southern Cross, Alpha and Beta Centauri, Achernar here, Canopus. Now we calculate the landscape, moving landscape, with a black hole passing exactly in the middle of the large Magellan cloud. So a simulation done by Alain in 2006. This is the movie. So you see a lot of stars here because it's inside the sun ring. So this is the duplication of all the bright stars of the celestial sphere. Here you have exactly the sun ring, and the black hole passes, and again you have separated image, but double image, primary image, secondary image of the large Magellan cloud. The same for the small Magellan clouds, and all the stars are duplicated. Okay, so this has been done a few years ago, and maybe some of you have seen this picture that are available on the web. But now, you have not seen the rest of the end of my talk, because this is a very, very, very recent and unpublished work done by Alain Riazuelo. And so to finish the dinner, I propose you a journey into a Kerr black hole. Realistic journey, more or less realistic, because it's an idealized Kerr black hole. So as you know, the Kerr black hole has a more complex structure with a ring singularity, which can be avoided by some trajectories. So you can have trajectory crossing the event horizon, passing above the plane of the disk and leaving the black hole through a wormhole. But you can also have trajectory passing through the rings and going into a kind of negative universe, asymptotically flat universe inside the black hole. So you know that the best way to represent the complex structure of an ideal Kerr black hole is the Penrose Cardiogram. Okay, so as you know, it's a conformal diagram where infinity is just here. Okay, so this is our universe, asymptotically flat space-time. This is a Kerr black hole with a different part. Okay, so and here you have other universe, which can be by topological consideration identified with our own universe. Okay, so you know that here you have the ring singularity, and you have two event horizons. You have the outer event horizon, which is really the real frontier of the black hole, and you have an inner event horizon. Okay, now we are going to a flight into a Kerr black hole with this angular momentum. It's not really extremal, but it's spinning at a fairly high rate. So it's a completely new calculation by Alain Riazuelo, still unpublished. So I will show you the landscape calculated step by step along this kind of trajectory. So it's a plunging trajectory, starting from our universe, outside, of course, the Kerr black hole, plunging into the black hole, crossing the two event horizon, crossing the ring singularity, and finishing in the infinite space inside the black hole, but with negative gravity. Okay? So we start the view here at r equals 6m. What we see? This. Alors here you have the view of our universe. Of course, you have the Milky Way. So Alain used, as in the previous calculation, the two-mass map of the sky here. So just you see this, but of course distorted by the gravitational lens. Okay, so this is just the view of our universe. But you see also something else, this part. And you see, in fact, the region here, -7. Why? Because you have some light ray trajectories, such as that one, okay, coming from the past, and which give a view of this universe, okay, which is represented here by this picture. All right, now we progress. We just crossed the event horizon, the outer event horizon. So we are inside the black hole. So what we see in B, here. Yes, because the outer event horizon is at this radial distance, and here you are just inside, okay? So now in B, what we see in B is this. So we still see the external space-time, because of course you have still the past light cone coming from the infinity, so giving an image of the full universe, more and more distorted. And here you have complicated things, which is black for some reasons. Okay. Now what we see in C, so we have crossed part of the black hole and we approach the second event horizon, the inner event horizon. What we see in C, we see this. So we still see our universe, of course, just due to the past light cone. So you have still information from the starting universe, even here. And it's more and more distorted, of course. So this is the two-mass map, very distorted. But here, you appear something new, which is in fact region 3, which is in fact represented by, well, we make the hypothesis that in the region 3, we had also a kind of map, okay? And this map is used to calculate the distorted result coming from this kind of trajectory. For coming from region 3, you have photon trajectory passing through C, okay, crossing the black hole, crossing the wormhole, and going into universe 11. So this is the view in point C. Now we have crossed the inner horizon. We are in point D, close to the singularity. What we see in D, we see this. Now we have 3 regions. Always our universe, because you have always the light cones. You see, yes, this kind of trajectory, okay, gives you this image. Now you see region 3 always, okay, with this kind of trajectory. And this, well, you can see something coming from region 7 here. This is the negative universe on the other side of the ring singularity. Because you have trajectory coming from this part in your past light cone, which gave also this image. And we have assumed that we have a kind of cosmic microwave background in this negative universe, and you have here the image. And now, since we are very close to the ring singularity, we can ask, where is it, this ring singularity? So we can see the ring singularity. It is here. Very thin line here. Okay, this is the ring singularity. So finally, we cross the singularity, and we are on the other side, in the negative universe. So what we see in this point is this. We still see the starting universe, and namely region 1. And essentially here we see region 7, namely a trajectory coming from this part, this negative universe. And finally, we are in the negative universe, and what we see in F is essentially this. We see essentially the supposed cosmic microwave background of region 7, the universe in which we are now, negative universe. And we still see here something coming from the starting universe. So you still have a memory of your starting universe. So this is this new calculation of a flight into a Kerr black hole. And now Alain is calculating the same picture for a trajectory, not crossing the annular ring, but just passing through the wormhole and going, that doesn't work no more, and going into region 11 or 9. Okay, so really going out of the black hole through the wormhole, and so we will have soon the picture. All right, so it's finished for this this travel. So I thank you with this funny picture. I disappear into a black hole. So I hope you have enjoyed, but really I want to insist that I'm deeply honored to be among you. So glad to see the realization of one of my dreams. Well, in fact, it was not a dream, but because in 1979, I never expected that in my lifetime I would see a real telescopic image. One of the reasons is that I'm a pure theorist. I'm completely ignorant in experimental things. At the time, I never heard about the VLBI, so I could not imagine that we could have a network of telescopes to see the biggest black hole, even if I predicted that maybe the main target, the first target, could be already M87. Thank you.
Thank you very much, Jean-Pierre. Can you just translate what this man is saying?
We can hear you, GP.
Okay.
It cuts.
Okay.
Communication is cut.
Just wanted to mention that Jean-Pierre was extremely productive some 40 years ago, the paper that you wrote. He also has a child that is 1 year old, which is quite remarkable. And we will take a couple of questions, if there are any from the audience. Yes, Maciek.
Why did you mention the 87? That's so great, but did you know that
Why don't you
So my question is, why did you mention M87 in the paper? Did you know actually the estimate of the distance and mass at that time? Why would that be a candidate to be mentioned in a paper?
For M87? Yeah. You mean? Because at the time we had already some measurement of stellar dynamics by Jung and collaborator in a paper in 1977. Suggesting the probably presence, just to explain the stellar dynamics of a black hole of about, at the time it was 5 billion solar masses. First of all. Second, it was not, M87 was not considered as an active galactic nucleus. So rather quiescent black holes, so plausibly surrounded by accretion disk, but not very high accretion rate. So maybe a thin accretion disk. So it appeared to be a good target, a good candidate. Huh? Well.
Any other question? If not, let's thank Jean-Pierre for a beautiful presentation.